Yes. Okay, so our next presenter is Reinier from Deakin University. Please, Reinier, go ahead.
Okay, thank you very much to the organizing, which I make part. Thank you, Julian, for being the chair of this section. My talk today is a joint work with Vera Rashina from the University of New South Wales. And I will talk about the intrinsic core and minimal phase of convex set in general vector spaces. The idea of the talk is try to make a relationship between the minimal phase and the intrinsic core of the convex set in the most general setting that we could do this kind of relationship. Probably there are more general than that, but was what we did. Okay, this is the index, and I will introduce which is the phases of a convex set, which is the minimal phase. I will talk in the section 2 about the intrinsic core and just summarize some topics that we will talk today. Okay, the definition of a phase is a classical one, and there is nothing new here. A convex set will be a phase of a convex set will be such point on the x belongs to the phase of the convex set if for every 2 points on C such that x belong in the interior of the line between y and z, then f will be a phase if these 2 points also belong to f. Okay, in this way we define the phase of a convex set, and this is some example in two-dimensional spaces. Given a triangle, for example, the points are faces, the lines or that make the triangles the sides of the triangle, and the whole space, of course, and also the empty space. The empty space always will be a phase. In this other set, we have that all these points in here are faces, as well as these 2 lines and the point. Of course, the empty set and the whole space are also faces. Okay, from the definition of phases, sorry, from the definition of phases, we have this lemma, this result that the intersection of phases that are phases of some convex sets, the intersection of all of them will be also a phase. Okay, and based on this result, that the intersection of any family of phases of a convex set is also a phase of this convex set, we can define the minimal phase. The minimal phase that contains some sets S. This set also could be a point, and we will talking about more about when the minimal phase is related to the point. Then the minimal phase of a convex set C, which contains the set S, which could be anything inside C, they will be the intersection, as we saw in the previous result. This will be a phase as well, and then the minimal phase will be the intersection of all the phases that contains S. Okay, then this result is well defined, and when this S is just 1 point, it's a singleton, then we will write, instead of this notation, we will just put f of the point, the minimal phase of x related to the set C. Okay. And the idea of this talk is relate, as I said, make some relationship between intrinsic core and phases, more specifically minimal phases. Then we will use this kind of this result, this one and the next one, that relate the minimal phase of a convex set of a point in the convex set C, it will be the intersection of the linearity space of the cone of the feasibility direction C minus X plus C plus X. Okay, then we prove on our paper. Of course, because of the time, I cannot make any proof here, but you are invited to see the paper. At the end, I will say where you can find it, and the minimal phase of the point coincide with this set here. Okay, then the minimal phase consists that is saying is consists precisely in the line, the segment for which that point X is in the interior of this segment. In other words, we can say that we prove that the minimal phase of a convex of a point in a convex set C is the union of all lines inside C, of course, such that X belongs to the interior of the endpoint of these lines. Okay, then we can see the minimal phase of a set as the union of many lines inside the set C that contain the point X in the mirror or in the interior. Okay, then okay, and this is a characterization also of the minimal phase, and it will be very useful to prove some result in the next as we will see next. Okay, the intrinsic core, we will present some definition, and we will present the definition of that intrinsic core in many settings, or we will try to give a different definition about this of this intrinsic core, that all of them are, of course, equivalent. Now, in infinite dimensional spaces, the relative interior of a convex set is defined with respect to the affine hull of set. Okay, and then this intrinsic core, it will be a generalization when we go from finite dimensional spaces to more general ones. In fact, when we are going to vector spaces with infinite dimensionals, with infinite dimensional spaces. Okay, then the first definition that we can see is that the intrinsic core, these definitions via the line segment, is using ideas, and they will be useful also for proof the equivalence with other definition that will be made today. And this definition said that the intrinsic core of a convex set in any vector space, real vector space, are all the points such that you can extend, given any point on C, you can extend in the side of X such that we can extend the line between the point and any other points in the set C, but beyond of X. And then you can say that for all Y on C, there exists set such that X is in the mirror or the interior of the line between Y and Z. Okay, then this is the characterization. You can extend for a point will be in the intrinsic core of C. If you can extend for any point on C, you can extend the line between these 2 points beyond on C, on X, okay? Beyond the point X. This is one definition. Proposition that is a consequence of this definition is that the intrinsic core is, of course, is a convex set, okay? Given any vector space and any convex set C, the intrinsic core will be, of course, a convex set, okay? But what's happened with intrinsic core, that not all the sets, the intrinsic core is different from the empty space. This is one example for which the intrinsic core is empty. Okay, on the paper we prove that this is true, that we have that the intrinsic core of this set C00 is all the sequence in infinite dimensional space. We have a finite number of non-zero entries. So just a finite number of non-zero entry, and the remainder is all zero. Okay. Then we prove that given any set on C, we can find a Y for which here we change the notation. Probably we can say that for any Y on C, we can find a set such that this guy will not be inside, and then the intrinsic core will be empty for any points that you pick on the set C. Okay, on the paper we prove that, and we give which is the face of this Y. Okay, which is the face of this Y. Given any points X, we can find this guy for which you cannot extend. You cannot have X inside these 2 points. Okay, that is why these sets have empty intrinsic core, and that as this set is empty, of course, that proves that not all the sets have not empty intrinsic core. Then we cannot ensure that the intrinsic core of a subset of a set, if you have A and B, that are 2 convex sets, and A is a subset of B, then we cannot ensure that the intrinsic core of A will be a subset of the intrinsic core of B. Just taking this set, for example, any point, and then this point belongs to this set C, the intrinsic core of the point, as we can see here, the intrinsic core of the point will be exactly this point, and this point cannot be inside the empty set. Okay, good. Some other properties that intrinsic core satisfies is that given any convex set in the real vector space, a point is in the intrinsic core, and for any Y in this set C, then there exists Z in the intrinsic core such that X belongs to this line, and all this line, the set, the line between Z and Y, for any Y on C, you have that these guys belong to the intrinsic core. In fact, particularly we have that for any point X on the intrinsic core, the line open in Y not need to contain Y, because Y could be in the frontier, on the boundary. Then the line, the whole line between X and any point on C belongs to intrinsic core. Okay, that can give us that the intrinsic core, if you take the closure of the intrinsic core, of course, if the intrinsic core is not empty, the closure of intrinsic core will contain the set C. Okay. Another property is that if you take the intrinsic core of the intrinsic core, you will not lose anything, then you will keep with the intrinsic core of C. It's like the same property of the interior. The interior of the interior is still the interior. In here is the same. The intrinsic core of the intrinsic core is exactly the intrinsic core. Okay. Good. Another proposition, another result, that given any set CS, and this will give a brief relationship between minimal phase and intrinsic core, given any set S on C, then C is a convex set. Then if S is such that the intrinsic core, S and C both are convex, is the intrinsic core of set of S is not empty, then for any guy that you pick in the intrinsic core of S, we will have that the minimal phase of this point is equal to the minimal phase of the whole set S on C. Okay, and as a result of this, we have that the intrinsic core of S is a subset of the intrinsic core of the minimal phase contained S and C. And in fact, this can be equals to the intrinsic score of the minimal phase of this point X when this point X is in the intrinsic score of S. Okay. Then when you have a set C, which is convex, if you want to see the minimal phase, you don't need to see the minimal phase of the whole set S. It's enough to pick a point which is in the intrinsic score of this S, and then you can see the minimal phase containing S as the minimal phase of in the same set C containing just the point X. Good. This is another definition which probably is the more classic or the classical one, which in the most of the literature you have that the intrinsic score of the point of the set C are all the points for which the cone of the feasibility directions are a linear space. Okay, this is the most common probably definition of intrinsic score, and of course we prove that they are equivalent. Now, a proposition directed from this definition, we have that given a convex set, then we have that this set, the cone of the feasibility direction, is a linear subspace if and only if every guy on C there exists, for every guy on C, there exists V inside C such that X belongs to U, the line between U and B in the interior, okay, which is equivalent with saying that X is in the intrinsic score of C, okay. This definition is this result is a consequence of this definition, okay. Okay, good. Another proposition, another result, and this will give us another definition of intrinsic score, is that the intrinsic score coincide exactly with the points for which the minimal phase are the whole set C. And this result is new, is one of the new results of this work, is the characterization of the intrinsic score given a minimal phases. Then the intrinsic score of a convex set, it will coincide with that point for which the minimal phase are the whole set C, okay? And this is the definition, another definition defining intrinsic score via or minimal phases. Given a set C, then the intrinsic score coincide exactly with this point due to this proposition. Okay, all this proof again we can find on the paper. Okay, due to this definition, we can see that for any convex set and any point on C, there is a unique phase for which X is in the intrinsic score of this phase. And consequently, we can decompose C as the union, this joint union, that is why this point, this joint union of the intrinsic score of phases of the set C. And this result is due to this definition and this other result, okay? And this is a very good, it's a nice result because we can see C and we can observe what happened with C only seeing his phases, okay? Then we can, of course, we can then call the problem of characterizing the convex set with not phase, which is called phaseless problem. And we have the following result: a set, a non-empty convex set in any vector space X is free of proper phases. See, I mean, the set C have not any proper phase. The only phase that it have is the whole set C if C coincide with the intrinsic core. It's like an open, if for example, if you take C as an open set, convex and open, then the only phase that it contains is itself. Okay. Good. Now I will present finalizing some calculus of intrinsic core, some properties that we can prove using that definition before, and say that the intrinsic core of the sum of two sets, convex sets, is included in the intrinsic core of the sum, and even more, if both have not empty intrinsic core, then we will have the intrinsic core of the sum is exactly the intrinsic core of each of the two sets involved. Okay. Another proposition due to exactly this property is that if we have a set C is convex, then for any guy on X, the intrinsic core of the sum of C plus the set, the singleton set X, is exactly the intrinsic core of C plus the intrinsic core of the point, which is exactly X. Okay. Good. Another properties, if you have a linear space, or sorry, a linear mapping between X and Y are two vector spaces, then if you consider A of the intrinsic core of any convex set, you will have that the application of the mapping, of linear mapping A, in the intrinsic core, it will be inside the intrinsic core of the application of A on C. Okay. With A, the application of A of a set, it will be the union of f of X for all X on C. Okay. I didn't say write it, but it is exactly that. Moreover, if the map A to AC, sorry, if A map C to AC is injectively, let's see, if the map is injective or the intrinsic core of set of C is not empty, then we have the inequality. So in general, we have this inclusion that if A is injective or if C have not empty intrinsic core, then this become in an inequality. Equality. Both sets are equals. Okay. As consequence, we have substituting A by lambda C, lambda X, A of X is lambda X. Then we have that the intrinsic core of lambda C, it will be, put lambda outside, it will be equals to lambda intrinsic core of C. Okay. And the intrinsic core of the product of two sets, it will be equal to the product of intrinsic core of the two sets. Of course, lambda cannot be 0, okay? Otherwise, it will not be injective. Okay, summarizing, we have presented some definition and property of intrinsic core. We give 3 property or 3 ways to define the intrinsic core via light segment, via the cone of feasibility directions, and term of minimal phase. On the paper, we also give a definition using the core of the affine hull of C, but because of the time, just 30 minutes, we don't present in here. Sorry, you have here some bibliography, this paper from Radu and Robert and Wanka, John Browy and Gober, Browy and Lewis, and this is the paper in which all the results are proven and other results are presented. It's a paper of this year, it's on archive yet. And thank you very much. I'm open for any question, any problem, or any that you can ask me. Yes.
We have already one question. Thank you, Reinier, for the presentation. We already have one hand raised by Alex, I believe.
Yes,
Alex, thank you, Reinier. Nice presentation. I like these beautiful things. This topic about convexity without topology, it was very popular around 1960s, maybe a bit earlier. And it's good that the topic comes back to life. My very naive question in the very beginning of your presentation, when you defined the intrinsic core, you also mentioned the word closure. I'm just curious, what did you mean when talking about closure?
Where I told the closure?
No, it was a bit further when you started talking about intrinsic core, and you characterized it in terms of segments, and maybe a bit further, there was a semi-open segment somewhere from a point in the core to an arbitrary.
No, it was sorry.
So you didn't mean it. You didn't mean it.
Yeah. Where is it? Here. This one?
Yes. Yes.
Yeah, this is the line. It's not the closure of the line. It's just the line containing X as an initial point, but without Y on the.
So the closure of the segment
is not the closure at all, because Y is not belonging in this set. You can see this guy of all the points in the way alpha X plus 1 minus alpha Y, with alpha between 0, not in 0, but containing 1.
Okay, so and a question related to this one. Why not defining the closure this way? It is looking at this proposition, I think it is natural to provide the definition of the closure. So is it related to some topology? Doesn't make sense to talk about topology?
Yeah. Vera, you want to, you raise your hands.
You are transferring the question.
Vera is trying to.
Yeah, I just wanted to respond to Alex, because somehow that part was algebraic closure. I think I was doing maybe a little bit more on that part, and also that part has more mistakes. So it's you cannot kind of define algebraic topology, but you can talk about algebraic closure of the set. So again, you are without topology, and it's there's really fine things, and Alex is really on top of things, because that's exactly what the referee told us, that we should have a look at the papers written in the 1950s.
Yeah,
and it was a brilliant suggestion, because the difference between our review paper and what happened in the 1950s is that they didn't look at facial structure so much. And there is the very recent research looks at facial structure, but nevertheless, so you can talk about algebraic closure, and algebraic closure means that all line segments in the set should be included along with the endpoint. And the fine thing here is something that I found really surprising, but maybe for Alex it's not surprising. The very fine things here is that if you take a convex set and you simply close all line segments, that is not the same as the algebraic closure, and the difference is really quite fine. So there's a lot of results by Klee about this kind of thing.
Yeah.
Okay.
So yeah, so it's absolutely fascinating. It's just such a cool topic. So I hope to learn more, and that we will be, doing more research in this direction.
Yeah.
I just want to make a disclaimer that I wasn't a reviewer for your paper.
So it's very good to know that there's other competent people in the field, Alex.
So there is one more.
Yeah, that is good.
We have two good reports. Reinier, actually, they just sent the official report.
Okay,
yeah.
no worries.
Yeah.
Okay.
So we have at least three competent people in this field. Very good.
That's good.
Congratulations.
Thank you, Alex.
Thank you, Reinier and Vera and Alex for the discussion. Any other question? We'll have time maybe for one more. Looks like not, so please join me to thank Reinier for the nice presentation.